Hello, dear student. Myself, Dr. Surekha Jaiswal, Moreshwar College, Bhokardan, District, Jalna. Today we will see mechanics, properties of matter and sound in elasticity. Course code number Phy101. Now, contents are cantilever loaded at free end having points, that is when weight of beam is ineffective and weight of beam is effective. Now, cantilever loaded at free end. Definition, that is, it is a beam fixed horizontally at one end and loaded at the other. Now let us consider a cantilever which consists of a bar of uniform cross section of length L. One end of the bar is fixed to the table and other end is free. Now let weight W equal to mg suspended at free end. Then there are two cases. First, assume that the cantilever to be weightless. And second case is the cantilever to be weighted. In these two cases, requires to find the Young modulus. Now see, let PQ is a small segment of cantilever and R is its radius. See in figure, this PQ having the, let X be the distance between center of PQ. See in figure, this small x is the distance between this P and Q. Have end A, fixed end A. Now AB dash shows final position of neutral axis of the bar. Now we have bending moment for PQ is, bending moment is given by capital M equal to Y into Ig upon R, where M equal to bending moment, Y is the Young modulus, Ig is the geometrical moment of inertia and R is the radius of arc. Now since depression moment of force W for section PQ is given by external depression moment equal to W into L minus X. In the equilibrium state, bending moment of PQ equal to external depression moment. So here bending moment of PQ is given by Y into Ig upon R and external depression moment is given by W into L minus X. So we know that 1 upon R equal to d2 y by dx square, that is curvature of beam or bar, and therefore equation 2 becomes d2y by dx square equal to W upon y into Ig into L minus X. So integrating equation 3 with respect to X, we get integral of this d2y by dx square into dx equal to W, integral of W upon y into Ig into L minus X dx. So here taking the constant quantity outside, that is W upon y into Ig integral of L minus X into dx, so is equal to W upon y into Ig Lx minus x square upon 2 plus k1. Now to find the constant of integration k1 in equation 4, we get at x equal to 0, that is at A depression is 0. Therefore tan theta equal to dy by dx equal to 0. Therefore theta equal to 0 and k1 equal to 0. So dy by dx equal to W upon y into Ig into Lx minus x square upon 2. Now to find the value of y of depression at x from A, we again integrate the equation 5. We get, therefore integral of dy by dx is y is equal to W upon y into Ig integral of Lx minus x square upon 2 into dx. So here therefore y equal to W upon y into Ig integral of Lx minus x square upon 2 dx is Lx square upon 2 minus x cube upon 3 into 2 plus k2. So simplifying, W upon y into Ig into Lx square upon 2 minus x cube upon 6 plus k2. Now again x equal to 0, y equal to 0, we get k2 equal to 0. Therefore y equal to W upon y into Ig into Lx square upon 2 minus x cube upon 6. This is depression at distance x from A. Hence, depression of B to B dash can be obtained by substituting here x equal to L. So, yb equal to w upon y into ig L cube upon 2 minus L cube upon 6. So, therefore, yb equal to, after simplification, w upon y into ig into L cube upon 3. This is the formula for depression of weightless cantilever when loaded at weight W at free end. Now, if the cantilever is in the form of rectangular bar of the breadth B and thickness D, the geometrical moment of inertia is given by Ig equal to B into D cube upon 12. So, therefore, Yb equal to W upon Y into BD cube upon 12 into L cube upon 3. After simplification, we get Yb equal to 4WL cube upon YBD cube. Therefore, Y equal to 4WL cube upon YB into BD cube. And this is equation 2. Calculate M modulus of cantilever using bar of rectangular cross section, and that is, if the cross section is circular, then Ig equal to pi r raised to 4 upon 4, and therefore Yb equal to W upon Y into pi r raised to 4 upon 4 into L cube upon 3, and therefore Yb equal to 4 upon 3 into WL cube upon Y pi r raised to 4. Therefore, y equal to 4 by 3 into W L cube upon y pi r raised to 4. Now, see the second case when weight of beam is effective. In the first case, depression moment was only due to the applied weight W. In this case, weight of the cantilever W1 also contribute to the depression. So, consider a small section of length dx at P. It will be depressed by applying loading weight W at the free end and B of the cantilever. In this case, we also consider that the weight of the cantilever W1 due to the weight of the cantilever, there is additional force which is give the depression moment at P, and this force F is due to weight of section of cantilever of the length L minus x and acting on the midpoint N. Now, weight per unit length of cantilever is equal to W1 upon L. So, F equal to weight of section of length L minus x. Therefore, F equal to weight per unit length into sectional length. So, therefore, F equal to W1 upon L into L minus x. So, here this force F is acting at the midpoint N. Therefore, the length of the bar between P and N point is L minus x upon 2. The moment of the force F is at about point N equal to F into L minus x, and the moment of force F at out point will be given by F into L minus x upon 2. Therefore, using equation 1, we can write as W1 upon L into L minus x into L minus x upon 2. So, we get W1 L minus x raised to x square upon 2L, and the moment of weight W about P will be given by W into L minus x. So, thus we have to find the total depression moment about P. Therefore, total depression moment about P equal to moment of force into plus moment of weight. So, here moment of force equal to W1 into L minus x raised to upon 2L plus W into L minus x, but we know that the bending moment M equal to Y upon R into Ig, where Y is the Young modulus, R is the radius of curvature at P, Ig is the geometrical moment of inertia, and therefore the total depression moment about P is nothing but the bending momentum of the bar. Therefore, from equation 4 and 5 we can write the total depression moment about P equal to bending moment of bar. Therefore, y upon r into ig equal to w1 L minus x bracket square upon 2L plus w into L minus x. But we know that the formula for curvature of beam or bar is given by 1 upon r equal to d2y by dx square. So putting the value of 1 upon r, we get here y into ig into d2y by dx square equal to w1 L minus x bracket square upon 2L plus w into L minus x. So d2y by dx square equal to w1 L minus x bracket square upon 2L y into ig plus w into L minus x y into ig. So integrating equation, we get dy by dx equal to integral of w1 L minus x bracket square upon 2L y into ig into dx plus integral of w L minus x upon y into ig into dx. So taking the integration, we get dy by dx equal to w1 upon 2L y into ig into L square x minus 2L x square upon 2 plus x cube upon 3 plus w upon y into ig Lx minus x square upon 2 plus k1. The net depression YB at B and B is calculated by putting x equal to L in equation. We get y equal to W1 upon 2y into Ig into L into L raised to 4 upon 2 L raised to 4 upon 3 plus L raised to 4 upon 12 plus W upon y into Ig into L cube upon 2 minus L cube upon 6. So here y equal to W1 upon 2y into IGL into 6 raised to L raised to 4 minus 4 into L raised to 4 minus L raised to 4 upon 12 plus W upon y into Ig into 3L cube minus L cube upon 6. Therefore, y equal to, after simplification, we get L cube upon 3 into y into Ig into W plus 3 into W1 upon 8. Thank you.